What's happening in a chemical equilibrium? Sorry? Yeah, the chemicals are still changing. Reactants are changing into products. Products are changing into reactants. But do you have a net change in the amounts? No. Okay, but individual molecules are changing. There used to be like a nice little film back when I was in high school, but you know, it was on like a reel-to-reel, like, you know, the projector. We used to watch films like that. It was the 80s. Okay. Anyway, and it had this thing where you had some H2 and you had some I2 and you had some HI, and you would put all of those into a flask together, but you would make this I2 radioactive. Yeah? So you would put them all together. So this would be like H2 and I2, and you would start with all of, and this one here, this I is non-radioactive. Yeah, and over time, what would happen is that you would end up in your flask at the start, you would have I bonded to I, little radioactive ones. You'd have H bonded to H, and you would have HI. Now, over time, you would end up with some, and obviously there'd be like 1,000 million more particles than this, 1,000 billion, trillion, quadrillion more particles than this, but you would end up with some of the HI having radioactive iodine in it because it would undergo the reaction, right? The I2 would undergo the reaction with H2 to form HI with radioactive iodine. And some of the regular iodine would then become part of the I2. Does that make sense? Did you have a question? So overall, you're still reacting, right? And they'll just be swapping out. So let's say we have all of our pens here. And I've got what? H2. And I got I2. And I've got 2 HIs. Yeah? Now, this one is my I2, yes. This one's radioactive. Yeah? Let's get rid of these ones because they don't match color. Okay? So I had H2, I got I2, I got HI, and as time goes on, some of the H2 and I2 are going to react to form HI. No, they were like this to start with. Some of them are going to react to form H2 and I2. My HI has just turned into H2 and I2. And my I2 and my H2 will turn into HI because that reaction happens at the same speed as that other reaction. And now you can see I've now got HI that has some radioactive stuff in it, right? And now my I2 is non-radioactive, but it wouldn't just be one particle. It would be like some of them would end up. So you would end up with 50% of, you know, on average, 50% of the particles would be one or the other. Something like that anyway. Is that okay, Tony? Okay, cool. Alrighty. So that is a dynamic equilibrium because things are constantly changing. Particles are constantly switching partners. All right. And that's why it is dynamic, because the reaction has not stopped. That's why it is dynamic. The forward and reverse reaction continue to take place. That is why it is dynamic. But their rates are equal. So there will be no changes in concentration. So yesterday, you remember when I said I didn't want to define dynamic equilibrium because I was like feeling like I did not have a good definition on top of my head? Dynamic equilibrium. Do I have it here somewhere? No. Is a reversible reaction where forward and reverse reactions continue to take place so changes occur on a microscopic level. That is sentence number 1. That explains the dynamic part. Now, if we want to explain the equilibrium, we need to say that those forward and reverse rates are equal. So the macroscopic properties stay the same. Did you guys catch the microscopic? Was that okay? Microscopic. We're good with that? Cool, cool. Okay. So this is part 2 of our definition. So that's the equilibrium part. The equilibrium part is that the rates are equal, so the macroscopic properties do not change. What the heck is macroscopic? Visible to the eye, okay? Large scale, observable, okay? That is macroscopic. And it is defined for you in the little box here. Macroscopic means large scale, visible, or observable. It is the opposite of microscopic. Now, when we say microscopic, we are not actually literally saying if you took a microscope, you'd be able to see the particles. That's ridiculous, okay? You would need like, I don't even know what kind of microscopy you would need to do. You'd need to do like X-ray things that I don't understand, okay? So the opposite of microscope, or particle level. Particle level is a better word for it, but usually people just say microscopic, okay? Which means too small to see. So the dynamic part of dynamic equilibrium is all about what's happening on the particle level. on the microscopic level. You have those little particles switching partners. Yeah? That's the dynamic part. The equilibrium part is where those two rates are equal so that you don't have any macroscopic changes, nothing observable changes. You look puzzled, Dorothy. It's okay? All right. Okay. So there appears to be nothing happening, but down at the level, particle level, all sorts of changes are happening. Yes? Okay. All right. What are some macroscopic properties? They are observable characteristics of a substance or system, and we already know one of them. The concentration is a macroscopic property. The total pressure is a macroscopic property. Color, temperature, density, pH. There are others, but this is a good list to start with, okay? You can observe color, you can observe temperature, you can observe density, you can observe pH. If no changes are made in conditions, do you remember what we called changes in conditions? We gave a word for that yesterday. That's called a stress. If no stresses were placed on the system, or no changes were made to the conditions, in other words, nothing is added, nothing's taken away, temperature remains the same, a system at equilibrium will remain that way forever. Forever. You will get a system at equilibrium that hasn't been that way forever, but it's been that way for 25 years. Actually, I lied to you. The temperature changes all the time, so this equilibrium does shift. But we've had these tubes for 25 years. This is actually the N2, this is NO2 in here. It's our brown gas, but it's mixed with N2O4, okay? And if I get a kettle going, I should get the kettle going, because then we could actually take a look at what happens when we change the temperature. Wouldn't that be nice? Shall we do that? Okay, I'm gonna get the kettle going. So dynamic equilibrium, two definitions there. Feel free to use whichever one you want. How do I open this? Do I just like run one? Yes, I do this. There are a few other things to consider before we summarize everything. Changing temperature will alter the rates. If we decrease temperature, what happens to the rates? Okay, I see people drawing, I see people on their phone, I see people playing like stand up their markers. What happens to rate when we decrease temperature? It decreases. Why does it decrease?
Because the particles are moving.
Particles are moving slower, so we get less collisions and less energetic collisions. So
less percent
with sufficient energy. Okay, excellent. Hopefully this kettle works. All right, while we wait for that to boil, changing the temperature alters the rates. For example, increasing temperature increases the rate. This is interesting. Increasing temperature increases the rate of the endothermic reaction more. than the exothermic reaction. Well, it has to increase one of them more, otherwise it wouldn't shift. If it increased the rates by the same amount, there would be no shift. But why? We'll take a look at that later. Okay, we need to do some kinetic energy diagram graphs for that. Okay, so for now, just believe me, it increases the energy of the endothermic reaction more. It has to do with the fact that the endothermic direction has a higher activation energy. Yeah?
So is it like if the temperature increases, the rate of the rate is more
Yes. If you decrease, the endothermic decreases more. The endothermic reaction's rate is always affected more. Okay, and that's because its activation energy is higher. So it has more effect. We can look at the graphs and look at percentages and things like that. I never feel really happy about my drawings of them though, so I'm going to see if I can find you guys some nice drawings if I don't already have them in here. Okay. And we might as well put that in here. Also, decreasing temperature slows the endo rate more. The endo rate is always affected more by temperature change. Is this boiling? Is it doing anything? Oh, it is. It's getting warm. That's exciting. Okay. So, in other words, if you're going to be at equilibrium, the temperature has to be constant because otherwise you're speeding up one rate more than the other. The rates are different and you're no longer at equilibrium. Letting material into or out of a system will affect the rates. So the equilibrium must be a closed system. That's number 2. And an equilibrium can be approached either by dumping reactants into a container and letting them form products and reaching an equilibrium, or you can dump the products into a container and let them form some reactants and reach another equilibrium. It is getting hotter. Okay. It's not making noise. My kettle at home makes noises. It sounds like it's doing something. I also need to get ice. Okay. Why would anyone put these back stacked together while they are still wet? I'm going to give the teachers some grace and assume it was some random, like, whatever you call them, student, peer tutor. But I don't know. Could have been a teacher. Ah. I'm like, don't stack them. Would you put your dishes away at home, like wet, stacked on one another? Gracious. Anyway. All right, so we're going to have one little dish here. If I can get this.
Really? They do?
Whoops. That was less than helpful. There it is. Okay. And I have a lab coat because then I'll be able to like hold this up in front of, oh, actually we've got a whiteboard right there. That'll work. So I don't need to put on lab coat. Because usually I'm over there and then I'm going to hold it up in front of my lab coat so you can see the color change, but we've got a whiteboard so we can just hold it up there. Now, would you agree that these are approximately the same color? I feel like this one's a little lighter.
Yeah, it is.
Do you guys think so too? Okay, so it's not just me. I'm not just crazy. Okay. Excellent.
Bro, the one on the left is lighter.
Yeah, the one on the left is lighter. L for left, L for lighter. Actually, no, we're going to change. No, that's okay. We won't change that. We'll just change which order these things are in. Okay. And because this is going to be like a horizontal process, I need some tongs.
I think I'm gonna read it.
Okay, that's good. It's okay. We'll make two. Make two. Work Okay, this is irritating because you can't do Okay. Here we go. Okay. Okay, now while we're waiting for that, ooh, look, you guys can fill this in. Can you guess what would happen if instead of having the colorless, starting with the colorless stuff, what if we started with pure NO2? If we started with pure NO2. Why you not work, Pen?
Oh. Let's try to.
The reverse rate would start out fast or slow? Fast. And the forward rate would start out not just slow, 0. Because we're starting with only this at the start. Now, as the reaction proceeds forward, what would happen to the forward rate? Forward rate would? Decrease? Increase. Well, the forward rate started out at 0. It cannot but increase.
The reverse would decrease.
Yep. And the reverse would decrease.
Eventually the two rates will become
The same. And equilibrium will be established. All right. Now, I finally got these. No, I don't. Okay, there we go. This one's not going to move? Okay. Oh, and I need water in this one. There we go. Hot water on the right. My left. right. So now I've forgotten which one was which. Let's see which one is lighter.
The left one.
The left one is lighter. Still, I think I got them. Yeah. Okay. Now let's see what happens. The left one is going into the hot water, and the right one is going into the ice water.
I can't see.
Don't worry, I'm going to take them out. Whoa! What just happened? The equilibrium was disturbed and we reached a
Higher rate.
new equilibrium. These will be going at a faster rate. Okay, I mean, obviously, if I take it out of the water, it won't be at an equilibrium because the temperature will change. But as long as I have it at the particular temperature, can I swap them now? Shall we?
You go back to where it was.
Maybe it's clear inside the water.
Woo! It takes a little longer to cool down, but still. I don't have quite enough water. It doesn't quite cover it. There we go. Ooh. Ooh, let's try just putting half of it in.
But if you let them just sit, like without like at the same, they just like they go back to the same.
They'll eventually go back to just the same. Okay, let's give it a second here. I'm just trying to submerge half the tube. Oh, look at that.
It's like half.
Oh, and this one's burbling away here. You can see the gas is sort of like going whoopity 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 whoop. I don't know. Is that the sound it makes? That's the sound it makes when I make it. Okay, because you can see the brown gas is being produced, right, by the bottom part of it. And then it kind of comes up into here and goes crazy. Yeah.
There was like color changing. It was like so you put it in the cold water, like for example, the water. But like it's not like
Sorry, I only understood one word in 3. I'm going to come over closer so I can hear you better.
So I like if you go to like lunch and put it in like cold water, but for example,
Yeah.
Oh, like bars and
Probably. That's a very good guess. Yeah. Do you know how in the summertime, not when there's like smoke from fires or whatever, but in the summertime, you'll often get like an orange haze over like the city, and you don't get that as much in the winter, right?
Is it usually pink?
Oh, it's pinky orangey kind of haze. Guess what that is? Ah, because cars produce nitrogen dioxide as a byproduct of burning their fuel. We try to get rid of it because it's like a toxic gas. You don't actually want to be breathing this. They do much better than they used to by having a catalytic converter that makes the reaction run more smoothly. So you get a lot less nitrogen dioxide being produced. But it used to be, especially in some place like Los Angeles, which is so heavily populated and so warm and has so many cars because it is a totally car-centric society, you would like descend upon Los Angeles and it would just be in this blanket of orange. It was really orange smog. It was really gross. It's not as bad because they've improved the fuel, they've improved the engines, they've got a lot of electric cars now, things like that, but still, that's what's happening. Now, question for you. We have our N2O4 and we have our NO2 at high temperature. Do we favor reactants or products? Remember, this is brown. At high temperature, here, I'll put this in high temperature again. At high temperature, do we favor reactants or products? Products. And I'm just going to put P for products. At low temperature, we favor reactants. I'm going to let you go through the mental gymnastics that it's going to require you to do to figure out if this reaction in the forward direction is endo or exothermic. You might want like another piece of paper for this. I don't know if you can cram it in here. I'm going to put it off to the side.
Yeah, that's what I said.
High temperature causes a shift in which direction? To the right. Yeah, because at a high temperature, it favors the products. Yeah, low temperature causes a shift left. Yes. Yeah. But we're just dealing with it the way it's written. Remember? No, it's not expected that you do that. In this case, that's how we have written it. But you could write it backwards and then it would be exothermic. Because it turned brown at high temperature. And so we're like, oh, look, we got lots of brown at high temperature. Yeah?
That's what I heard. No, that's genuinely what I heard. Okay, I accidentally thought it was honest with you. I want to start with this thing about always in case of this reaction.
Has anyone thought it through? What do you think?
Endo for the forward reaction.
Endo for the forward reaction. I hear from one person. Anyone agree with her? Woo, a bunch of people agree with her. Anyone have an opposing view? Okay, so I think you're right, because if we increase the temperature, we increase the rate of the forward or the endothermic more. And if we're shifting to the right, that means that we have increased. So we start at having the two rates equal. And then we increase the temperature, and both rates increase, but the forward rate increases more than the reverse rate, and that's going to give us our shift. To the right. And then at the end, new equilibrium, we will now have both rates faster than before. Is good? Yeah? No. It depends. Like if you were to write this reaction backwards, it would be the other way. It's just in this specific case. Is the forward reaction in this specific case? It's not always, the forward isn't always endo, but you would have to figure it out on a case-by-case basis based upon your observations, right? You would have to say, oh, when I put it into hot water, it turned dark brown. When I put it into cold water, it turned light brown. Therefore, high temperature must have been causing it to shift to the right. Low temperature must have been causing it to shift to the left, the way the reaction is written now. It would be backwards if we had written the reaction backwards. Is good? Yeah? Okay. Now, do you have to go through all these mental gymnastics every time? No, you don't. Okay? There is a way of predicting them that makes your life very much easier, and that's called LeChatelier's principle, and there's a poster up there about it. And basically, it's a principle. It's not a reason. This thing about the rates here, this is the reason it shifts to the right when you heat it. Okay, this is the reason it shifts in the endothermic direction when you heat it. Yeah, it shifts in the endothermic direction when you heat it. Always. Yes?
So in this case, where it's up high, in this case, where it's up high.
Yeah.
So then,
if we had the other way around, we would still shift in the endothermic direction if we heat it. Anytime we heat a reaction, it will shift in the endothermic direction. Anytime we cool a reaction, it will shift in the exothermic direction.
I thought, like, it affects like this game, so like one is just one.
Yeah. But that means that we will be shifting in a direction because one of the rates is going to be bigger than the other. Right? So this is endo. This is exo. This is endo. This is exo. When we increase the temperature, the endo rate increases more.
But how do we know that the endo rate?
Because we are shifting to the right because it turned dark brown. At a high temperature, it turned dark brown. Okay, so you have to make your observation and say, it is dark brown, therefore it has shifted to the right. And if it is shifting to the right, that means that the forward rate must have been faster than the reverse rate. Because if the reverse rate were faster than the forward rate, we'd be shifting to the left. Yes? Yes, that is a general rule, and when you decrease it, it also affects the endothermic reaction more. So the endo will slow down more when cool, it will speed up more when heat. General rule, yeah. So anytime we increase temperature, the endo speeds up more than the exo. And therefore, we will shift in the endothermic direction because the endothermic direction will be faster. So let's say, just so we have a counter example, let's say we had our initial, right? And let's say that this one is, the backwards one is endothermic this time, and the forwards one is exothermic. Now, when we increase the temperature, what happens to both rates? Both increase. Which one increases more, forward or reverse in this case? Reverse in this case, because in this case, the reverse is endo. Endo rate increases more. And so the exo also increases, just not as much. And then our new equilibrium, we would have both rates being bigger than they were before. But this process here, because that was supposed to be highlighted, not scribbling. There we go. Because that reverse rate is faster. In this case, we would be shifting left. How do we feel about that? Good-ish? Okay. Now, you can just remember that an increase in temperature always favors the endothermic reaction. Yeah? You will always shift in the endothermic direction when you increase temperature. Okay? Okay, so it's always going to favor the endothermic direction. Okay, so if the endothermic direction is going to the right, it'll favor the right. If the endothermic direction is going to the left, it'll favor the left. Is good? Okay. Do we need to write all of this for lowering the temperature? It's the same except for the opposite. The endo will slow down more. Well, let's write a little bit of it, okay? When we decrease temperature, the endo slows more. Therefore, the endo is going to be slower than the exo. In other words, the exo is faster. Yeah? And if the exo is faster, then we are shifting in the exothermic direction. A decrease in temperature always favors the exothermic reaction. So if we had our old equilibrium, and this was, the forward was endo and the reverse was exo, and then we decrease the temperature, then the forward rate would slow more. So it would be teeny tiny, and the reverse rate would slow, but not as much. And then our new equilibrium, so the endo slowed more than the exo. This is the real reason why things are shifting the way they do. It's because one rate is faster than the other rate. But you can explain this if you are asked to explain it in terms of LeChatelier's principle. You can say, LeChatelier's principle says, in general, never give this as the explanation. Whatever you do to a system, nature tries to undo. Okay? But never give that as an explanation, because is nature really trying to undo anything? No. Okay? But if you're asked to explain in LeChatelier's principle, you can say, if I decrease the temperature, the system will shift to release heat to bring the temperature back up. That is LeChatelier's principle. What we did, we decreased the temperature. Now the reaction is going to shift to increase the temperature. Okay? I'm getting way ahead of myself, but that's okay. LeChatelier's principle. It is. And it's really funny because in the States, they call it LeChatelier. No, LeChatelier or something like that. LeChatelier, I don't know. Anyway, it's really awful. I'm like, oh my God, not that I have great pronunciation in French, but it's better than the Americans. Yeah. And like I said, this is a principle, not a real explanation. Yeah. Okay, we'll come. There's like a whole section on LeChatelier's principle, but I'm like, we're here anyway. We might as well do this. Says, when a stress is placed on a system, right? We make a change to the system. I miss the old days when I didn't have books and I just wrote freeform all the time. It was great. So when a stress is placed on a system, the system will shift in order to minimize that stress. So when we change the system will try to undo that change. It'll try to change it in the opposite direction. And you know why we have homeostasis so many times? Because of equilibria. It's like the buffer system in the blood is in equilibrium. Yeah? Look, biology and chemistry coming together in one. My favorite part of the whole thing. All right, so we have the system will shift to undo that change. So for example, if we increase the temperature, The system will shift in the exothermic direction to release, or sorry, if we increase the temperature, the system will shift to absorb heat to bring the temperature back down. And then, of course, and watch how we use dittos here to not have to write everything again. If we, ditto, ditto, if we decrease the temperature, the system will shift to release heat. In other words, the exo direction dir with little n is direction to bring the temperature back up. Is good? Okay. And the same thing is going to happen when we increase a concentration of something. If we increase a concentration, the system is going to shift to use up that thing. So if I add a reactant, it's going to shift towards the products. If I add a product, it's going to shift towards the reactants. If I remove a product, it's going to shift towards the products to make more of whatever I took away. Okay, that is what LeChatelier's principle tells us, but all of it comes back down to, in the end, it's really about the rates. Okay, so there are some questions in here. We'll leave those be. What time? Class over 11:35. We got 15 more minutes. Let's look at stresses and shifts. This is on page 24. Color is an example of what type of property? Macroscopic. Excellent. We have learned that word in context today. Okay. And what does macroscopic property mean? It is an observable. We've now used that word a few times today. We are making it our own. At equilibrium, those macroscopic properties are constant. And at equilibrium, what two things are equal? Forward rate, reverse rate. Okay, a system at equilibrium will remain at equilibrium until stressed. This is an important point. And a stress is a change that we make to the system. Okay, sometimes people think that any change is a stress. Well, if it's shifting, that's a shift, not a stress. Okay? Stresses always make the forward and reverse rates unequal. We are going to be graphing stresses, and that's what this one is all about, is about the graphing of the stresses. Stresses are considered for the purposes of a graph to be instantaneous. This makes graphing them easier. So if I change the temperature, I don't assume it takes, 5 seconds for it to get to the new temperature. I assume that happens immediately. Yes? If somehow I were able to inject some more, like say there was a rubber stopper in here and I put like a hypodermic needle in there and I injected some more product in there, that would be assumed to be instantaneous, happening in no time whatsoever. Okay? What? It is an assumption to make the graphing tidy. Okay? They are considered to be instantaneous. They take no time. This makes the graphs pretty. It's not because they actually take no time. It's because it's really ugly if you don't do it. So, on a concentration graph or on a rate graph, these show up as vertical spikes. So, we have here, let's say we had, what did I actually use as the example? That is a very good question. Okay, yeah, I did use that one. Okay, so here is a concentration graph. So on our y-axis is concentration. Guess what goes on the x-axis? That's going to be our time, okay? And we're going to use our favorite little reaction. We're going to use NO2 and N2O4. And you'll notice, are the concentrations equal? No. Should they be equal? No, but they are unchanging. What do we know about this system if the concentrations are constant? We are at equilibrium. Okay, so this is our original equilibrium. Now, let's say we, at time t, we add some N2O4. What would you expect to happen to the concentration of N2O4 at time t? It's going to increase as a vertical spike.
Oh.
Why is it a vertical spike? Because how much time does it take to do that? 0 time. Okay? Okay, we're making an assumption here, Tony. Can you just work with me on this? We're like, it's instantaneous to make the graph pretty. In fact, not just to make it pretty, to make it doable. It's ugly and it's not fun to graph if you try and make things realistic. Okay? So we're not going to try and be realistic. We're just going to be like, there we go. That was our increase in the concentration of N2O4, and it took no time at all. Okay? There we go. All right. We also have a rate diagram. So that's going to be rate versus time. And if we are originally at equilibrium, what do we know about the forward and reverse rate if we're at equilibrium to start with? They are the same. So we have the forward rate and we have the reverse rate. Now, all of you who are like picky people, oh my God, those aren't the same because they're not touching each other. You can't make them touch each other and still distinguish between them, okay? Do your best to make them look like they are the same, okay? Get over it. It's okay. We don't have to be perfect. We are not computers. We're doing the best we can with the tools we have. All right. Now, again, at time t, and we have our reaction, which is, in this case, N2O4 in equilibrium with 2NO2. And again, at time t, we add some N2O4. Which graph, which line, which rate changes? The reverse. Hang on. We added some N2O4. N2O4 is a reactant. So the forward rate changes. Okay, so the forward rate, how does it change? Does it go up or down? It goes up. How does it go up? Vertically. Because that change is instantaneous change. Changes due to stresses things that we changed are instantaneous. Or I could just say instant, but I'm going to say instantaneous. Huh? What? Yeah, so what I would do is, like, let's say there was a stopper. Like I said, if there was a stopper on the top of this, I could have some N2O4 in a hypodermic needle. I could jam the hypodermic needle through that stopper, press the thing, and Bob's your uncle. Yes? Yes. You would, after the vertical line, we're going to look at what happens next. Then we're going to draw the shift. So right now, all we've drawn is the stress. Then we're going to do the shift. Did that answer your question? Okay, cool. Okay, so this is just the stress. So stresses are vertical. So what things can be stresses? Well, a change in concentration. We've already done a change in temperature and a change in volume or pressure. All of those things are stresses. What things are not stresses? Adding a catalyst. And the reason adding a catalyst is not is because adding a catalyst speeds up the forward and reverse rate by the same amount. Changing surface area also speeds up the forward and reverse rate by the same amount. I'll show you. Just wait. I got a picture. I got to draw it. And an inert gas, adding an inert gas, increases pressure, but it doesn't change the concentrations of the reacting gases, so it doesn't affect the rate. So let us now go back to the surface area business. And let's imagine that we have a solution that is in equilibrium with its solid. Okay, do you guys remember having a saturated solution last year? We made a saturated solution way back at the beginning of the year. No. Okay, that's all right. I'm going to draw a picture for you. Okay, so we've got a saturated solution. I suppose I should write out the whole word the first time we use it. So it contains the maximum amount of dissolved solute. And it reaches an equilibrium. Where for every particle that dissolves, another one recrystallizes. Because once you've hit the maximum that can dissolve, it's not like the particles are going to stop dissolving, right? There's going to be water molecules bashing into the solid, freeing those ions, but the solution says, oh, I am full now. And therefore, some of the ions that are already in solution will then recrystallize. I like to think of saturation like being like a hotel, and you've got people waiting outside the hotel, right? And if you are unsaturated, that means the rooms in the hotel are not full. So people can just keep checking into the hotel. Yes? Now, people will check out from time to time, right? But you get people checking in and checking out and checking in and checking out. But eventually, if you've got lots and lots of people outside the hotel, that hotel is going to get full. Yes? Now, anytime someone wants to go into the hotel, in other words, dissolve, okay, someone has to check out of the hotel, in other words, recrystallize. Does that kind of make sense? Okay. So this is a situation where we have a surface, right? We could have a large surface where here's our beaker, and we have AgCl solid, and it dissolves into Ag plus and Cl minus. But then another particle, Ag plus and Cl minus, they will reform. Okay, and I'm not going to write all the ions, but you have the opportunity to dissolve not just over here, but you can dissolve here and here and here and here and here. So do we agree that the rate of dissolving has been increased by having a larger surface? We can also recrystallize here and here and here and here and here and here. So do we agree that we've also increased the rate? If we have a large surface, we have a faster rate of recrystallization because they're occurring at the same site. Can I put your homework on Teams? Then you don't have to wait for me. I'll come up with it now, so if anyone wants to stay, you can do that, but I'll throw it up on Teams so you don't have to wait for me. There will be some blue book and some pink book today.
Remember last year? It was softer inside.
How's the temperature in the room now?
Cold.
Isn't it better though?
Thing.
Okay.
Last year, I remember one time it was really cold during the winter dance, like next to us.
I remember that.
Yeah. I was like, I'm bringing a bunch. So good. Never changed. It's better. It feels so
It was like 1 year that they changed like this one, and then now it's really cool. Like,
Yeah.
Before that, it was like
before that, which was what in like grade 8. Bye. On sped.
Bye.
It's so funny, bro. All their funding is great. They're 84%. I feel like it's like it's just maybe that like
See you later.